go faster, you miss some of it, you can watch it again. Okay, science time. Today we're talking about systems and system models. Oftentimes we start these discussions by defining these things. Let's start with this one. What's a model? Do you know what a model is? Cameron, what's a supermodel, Cameron? No, what's a supermodel, Cameron? Do you guys like this discussion? What's a supermodel? No one knows. No one's ever heard of supermodel. You guys are 8th grade boys, all blushing up your necks, but you've never heard of supermodels before? What's a supermodel, Tristan? A famous person. No, but she or he.
Shows off clothes.
Yeah, okay, there you go. It's a person, a human being, so don't objectify them. It's a human being whose job it is to show you what clothes will look like. That's the idea. So a supermodel, we might as well just write this down. A supermodel is a person who shows, we're going to put another word after that, a person who shows what clothes look like. What's another word that I had here? Shows. What's another word we can use in there?
Displays.
I'm looking for another more specific one. Yeah, that's right, but that does what? Why is she called a supermodel? Because she models what clothes will look like. And this is getting at the idea that a model is as Aiden correctly says, a representation. Is she actually wearing the clothes? Yes. Is she showing you what the clothes look like? Yes. Is she showing you, as is the point, what the clothes will look like on you? Not necessarily, because it's an imperfect representation. The supermodel's job is to show you, ideally, the best, the way that society perceives these clothes should look. Yeah? That's what our models in the lab did. Was your model of the sun with your phone flashlight and the earth, which was a wiffle ball wrapped in clay, was that a perfect model of planet Earth? No. A great way you can check if that's a perfect model is, could you see Crawford, Nebraska on your globe? You can see where it would be, but you couldn't see Crawford itself. That's crazy. A perfect model of planet Earth would have every leaf on every tree, every feather on every bird, every molecule of sand on the beach. A perfect model would. A perfect supermodel would show what the clothes look like on every human being. Both of those things are clearly impossible. So the reason we use a model is to represent, however imperfectly, to represent, kind of to get the point across of a concept or a system without actually having to show the real thing. That's what a model does. So it's an imperfect representation. We could even say it's an approximation. Is the model perfect? No, so why use it? Why would exactly. If I'm going to, here, look, what's this? You can probably already tell what it is. Yeah, this is supposed to be Earth. If I was going to say, now class, fourth grade class, this is the country Brazil. Was this model perfect? Does it perfectly represent Brazil? No. But if you're 4th graders, does this do an okay job of telling you where Brazil is so you know where it is in comparison to the rest of the globe? Yeah. So a model doesn't have to be perfect for it to be useful. Did your model of lungs show how lungs work? Yes or no?
Yes.
Yeah. Was it perfect? No, of course not. It didn't show the pulmonary veins or the pulmonary arteries. It didn't show the bronchioles. It didn't show the alveoli. So it wasn't perfect. It wasn't complete. This word perfect actually means complete. It wasn't perfect, but it did a good job, in my opinion. It did a good job of showing how lungs work. They inflate and they deflate. So a model is an approximation or an imperfect representation of the way something is in order to get a point across. That's what a model is. Why would we use models? Give me 2 reasons. Aiden? Yeah, to represent something, maybe even something complex. It's actually, the human body is a complex thing. It's one of the most complex things we've ever seen in nature. To to represent it in a simple way so that even third graders can know what an appendix is or whatever is useful because it's a complex system that you don't have to understand fully to understand in part. Mason, what's another example of why we would use a model? Can anyone think of another model?
For like a human body, a model of it, so that we don't do it on the real scale thing.
Yeah. So we can show something like a cross section of the human body without having to actually have a human being up here that we cut in half lengthwise, because that would be gross. It would make a mess. So we can use a model like this, even if it's not very good, to show here's the brain stem, here's the brachial nerves, here's the solar plexus, right? We can show this model of the nervous system without having to actually have the mess of having a real guy up here displaying his nervous system, blood everywhere. Wouldn't be good, right? So there are some other practical considerations too as to why we would use a model. So these are both imperfect representations. They're both approximations, but they get the point across. For instance, here's the solar plexus I said. Did you know that the solar plexus was there? No, but my model, even though this is a stupid-looking gingerbread man, you now know where the solar plexus is, which you may not have walked in this room knowing, right? Because of the model. I'm going to erase both of these because they were examples, and we need to talk about something else. Do you have questions about models and why we would use models? No. Okay, so let's think about the systems in general. What's a system?
A series of things, how it works.
Yes. Okay, a series of things. You've seen these SEPs and CCCs before. Was your 6th grade teacher Mrs. Meininger? Yeah. Yeah, it's an organized group of related objects. Well, maybe she taught you 5th grade science.
Yeah,
5th grade science. But probably in 4th, 5th, and 6th grade you talked about all of those things. There are 8 SEPs, you can read them, and there are 7 CCCs. The CCC stands for cross-cutting concepts. Those are things that we use in all the sciences. Things like, look, one of them is systems and system models. You just saw an example of, I erased it a little bit too soon, but I had an anatomical system here, and here I have an astronomical system. Those are 2 different sciences, but they both have systems. We use systems and system models in all kinds of science. That's why it's a cross-cutting concept. It cuts across all the kinds of science. Tristan.
Our super teacher was
Miss Anderson. Okay, and she probably talked about CCCs, right? Cross-cutting concepts.
Fourth
No,
grade,
Miss Anderson was the math.
in fourth grade, we had Mrs. Meininger.
Okay.
Fifth grade, we had Mrs. Raven. Sixth grade.
Okay, but you did learn about these. You know what they are. We'll talk more about all of those things as the year progresses, but right now we're talking about systems and system models. So thinking about this system, it's a group of interrelated components acting together. I prefer acting together to working together. Working together makes it sound like they're really trying hard, like they're working at Dollar General, like they're making an effort, but that's not a conscious decision. In almost every system in the universe, the acting together is not conscious. You know what I mean by conscious? I mean like human beings think consciously. We think and we know we think. Right? Dogs think, but they don't know they think, or as far as we know. Fish think, but they don't know they think. Even trees probably, the evidence suggests, think to some capacity, but they don't know they do. Rocks certainly don't even think. Not only do they not know they think, they don't think. But they still act together. Right? That's why I prefer this to working together. Sometimes you might say they are things that work together. And that's true in some case, but I don't want you to get confused to think that they're all like coming together as a group to decide on something, because they're certainly not. Almost every system is non-conscious. So these components are like parts, and they act together. All right, is anyone going to write any of this down? They are interrelated, meaning that when one thing acts, another acts with it. For instance, if we had the buttes, you know the buttes from Crawford, Nebraska? The buttes are a system. They're a group of interrelated components acting together. Let me give you an example. Let's say there's a rainstorm on the buttes, as there was last night and kind of most of yesterday. And because of the rain, a little pebble here tumbles down the buttes and crashes into another pebble here, which tumbles down the buttes, and now we've got 2 pebbles in a pile that weren't there before. Does that seem like a feasible scenario to you? Of course, it probably happened millions of times yesterday. But these things interacted. The first pebble interacted with the rain, fell down, and not only did the second pebble get knocked loose, but it also interacted with the first pebble. It pushed back on it. They didn't stop. They both kept falling, but there was an interaction, a gravitational interaction. They acted together. Do you think this pebble thought, oh no, I'm slipping, and then fell down and said, oh, look out, buddy, and then the buddy didn't look out, and then they both fell down? No, they weren't working together by thinking. They were acting together in a physical sense. Physics was happening, and they didn't think about it at all. They're rocks, for crying out loud. But they did interact. They acted together. What was, in this specific case, let's talk now about this. What was an input?
The rain.
Rain. Were there more inputs? What else? Butte. We can say the height of the butte was an input. What else?
Rock.
Okay, rock. Yeah, what else? I'm going to put gravity. Gravity was the force that caused it to happen. What were some outputs? Yeah, falling. Verbs can be outputs. They're a little pile at the bottom. The erosion is what we call this whole process. That's an output. Do you think this in any way affected the rain?
No.
None? How did the rain get here in the first place? Do you guys remember the water cycle? What was this rain at one point? This rain was, yeah, evaporate. It was somewhere else. The water was somewhere else and it evaporated. Do you think in any way this little pile of rocks might change the rate of evaporation or the speed of evaporation? Probably at least a little bit. There's a weak interaction between not the rain in the past, but some future rain and this pile of rocks. Everything, here's the point. I have to put my marker down for this. Everything is interconnected. In the universe, everything is interconnected. Did Neptune in some way affect this? Yeah, maybe. I mean, the gravitational interactions between all the different planets when Earth was formed probably caused some change in this microcosmic system here. Everything is interconnected. Here's another reason. Everything is interconnected. Do you think this system in some way is interconnected? Do you think this system is in some way interconnected with the supermodel? Not in a way that we know, and certainly not like, it's not like these rocks changed something that back in time made it so she wasn't born or something. But the fact that I'm talking about a supermodel and this in the same sentence is an interaction. It's a very, very weak interaction again, but everything is interconnected. The same gravity that causes these rocks to fall causes the supermodel to be able to walk along a runway, right? This is not how you do a runway walk. But if there wasn't gravity, she would not be walking. She might do a runway float. There's a connection. Everything is interconnected. So that's another thing that is true of models, not supermodels this time, but of models, is that we cannot have a perfect representation of this, because a perfect representation of this system, the Earth, would incorporate the entire universe, because everything is universally connected. We can't display that. We have to pick the boundaries of this system. What are the boundaries? And who decides? What are the boundaries of planet Earth? Where does Earth stop and space begin? Where does the atmosphere stop? The atmosphere is not, unlike how I thought when I was a little kid, the atmosphere is not like a snow globe of glass hanging on to planet Earth. The atmosphere is a slowly fading cloud of gas. Where does the atmosphere stop? Some people say 100 miles. Some people say 60 miles. Some people say 1,000 miles. The fact that people are saying it, and that there's all these different confusing ways that it could be, human-made definitions mean that there is no solid boundary here. Where do you stop? Where is your boundary? You say it's your skin, right? That's the classic thing. Like, this is me, this is not. This is me, this is not. But is that T that was in here, is that me?
Yeah.
Is it? So there's at least some vague boundary. The boundaries are always vague, and they're always defined by, fill in the blank, who?
People.
People. They're always defined by people. What's a dog? Why is my dog a dog and a deer is not a dog? Because people said so. Because people said so. In fact, it's interesting I picked that word because the word deer originally just meant any animal. In the Old English, in like not Middle English, but Old English, deer was just a term for animal. And then the deer themselves were specifically called harts, H-A-R-T-S in Old English. And then eventually, since deer were so common, that word came to be used for those specific. But the point is that people defined what is a deer. If we ask that same question of someone in the 900s AD in Britain, and if I could speak Old English, and I said, why is my dog not a deer? They would say, your dog is a deer. Because the boundary is vague, and it's defined by people. Yes?
Do you know that in California, I think the bees are not fish?
Bees are now fish, yeah. Well, who says they're not? The word fish, this is getting a little bit philosophical and non-scientific, but the word fish is defined by people. So if people decide, as a group, that we're now going to call bees fish, that is truth. Just as much as bees are insects is truth to us now. It's always vague. Does that mean that systems and system models are useless because they're defined by people? No, of course not. So the fact that this T might now be part of me makes the system of me kind of vague. But if I go to the doctor and say, I have a tummy ache because I drank too much tea, they will know that I mean this system. They're not going to say, do you mean you or your dog or a deer? Because the systems are still, the boundaries are still useful. They're just vague. And it's kind of philosophical to determine where the systems end and where they begin. They're useful, but vague. Last thing we're going to talk about, is this a natural system or a created system? Natural. It's natural, and I don't mean created. What was the word I was supposed to use? There was a word that your explorations used. What was it called? Engineered. Is this a natural system or an engineered system? Natural. Natural or engineered? Natural. Natural or engineered? This is engineered. Human beings have made this system. What is the system here? What kind of things are working together? No, this is a digital watch. So there's a battery, there's a little piece of quartz in there that causes a piezoelectric current that makes the thing tick. There's probably a circuit board that causes this digital display to work. There's a light, there's buttons. All that stuff acts together because it's a system. But it was made that way by human beings. Where's the boundary of the system? Is my wrist part of this system? Kind of. I mean, you could make a case that it is. You could also make a case that it's not. It doesn't have this shape if it's not on my wrist, right? If it's not on my wrist, if it's over here, it's no longer that shape. And so my point is the systems, while the definitions are vague, are still useful. It's still useful to have this idea of a watch. What about my computer? Natural or engineered system? Engineered. What about a wheelbarrow full of dirt? Natural or engineered? Yeah, again, there's some vaguity, right? There's some vagueness about whether it's part of nature, like the dirt is. Even for about half a month, there was a pile of dirt in my lawn, just a pile of dirt about as tall as I am in my lawn. Was that a natural or an engineered system? Yeah, both, and it's possible that it is both. And then I want to highlight real quick this interrelatedness, that it's interactive, that nothing changes in a system without also changing other things. In the example you used for your bell work aid in the cardiovascular system, as we were talking, we were discovering that things like the digestive system impacts it, right? The skeletal muscular system impacts it. That's where the bone marrow makes the red blood cells. So they're all interconnected. Everything is interconnected. And where we decide to draw the lines is more or less up to people. There are some physical things. You know, your physical skin kind of separates you from the atmosphere. But if you get right down to it, on the cellular level, there is some gray area. Just like the atmosphere of planet Earth, there is some fuzzy boundaries that we decide, this is me, this is not. But there are some fuzzy boundaries. You have questions about any of this? This got kind of philosophical and kind of crazy. But as I said before, the idea is that you learn the basic and concrete concepts from this. This was supposed to be this, your explorations. Can you see it? It's upside down, but it will flip. You know what? I think I have the flip turned off. But the idea is that you learn the basic and concrete concepts from this, and then I will kind of fill in the gaps and give you, I don't know, I guess a sermon about how everything is interconnected. But I hope this was interesting to you. Do you have questions about any of this? Do you think this helped you with your understanding of the explorations? When is the quiz?